Math 1314, Section IC1, Spring 2022, Tyler Junior College, Section 3.3, Complex Numbers, Video 3, Adding and Subtracting Complex Numbers. In the previous video, we talked about simplifying square roots of negative numbers, which is kind of the genesis of complex numbers, or the genesis of imaginary numbers, which led to complex numbers. In the previous video, we talked about what an imaginary number was. In this video, we're going to talk about adding and subtracting complex numbers. I want you to remember that every real number is a complex number and every imaginary number is also a complex number. So as we have this discussion about adding and subtracting complex numbers, it also applies to real numbers and imaginary numbers as well. Let's start by recalling a couple of key concepts from the previous videos, starting with the fact that the imaginary unit, I'm going to highlight some things here. The imaginary unit I is defined to be the imaginary number whose square is -1. In other words, I does this. When you take I and square it, you get -1. Now, if you square root both sides, you could also say that that I equals the square root of -1. So there's really two ways to think about the imaginary unit I. By itself, it's the square root of -1. And when you square it, you get -1. I also want to remind you that these two equations, or statements, if you will, kind of tell you a couple of things to be on the lookout for when you're working with complex and imaginary numbers. The first of which is if you see I squared, if you see, and let's take this up a font size. I thought I would take it down, but I'd like it a little bit larger. There we go. If you see I squared, and I will put the square on that in just a second, change it to -1. But the second thing was, if you see the square root of -1, and I'll draw the square root over that in just a second, change it to I. Now we'll actually be doing neither of those things in this particular video, because in order to see I squared, we'll just draw the square. That's not a square. What is that? If you see I squared, you'll see I squared when you multiply. But this video is about adding and subtracting. But if you see I squared, you change it to -1. And if you see the square root of -1, you change it to I. So just a reminder about what the number I does. Also recall that a complex number, let's highlight that definition. A complex number is a number of the form A plus BI, where A and B are real numbers, so numbers you would find on a number line, and I is the imaginary unit. So let's talk about adding and subtracting complex numbers. Addition of complex numbers. Let's start with a really simple problem, one that you could probably do without me explaining a thing. Add 3 plus 4i and 5 minus 7i. Keep in mind that these two things, which look like unfinished problems, are complex numbers. They're the correct form of something plus something I. And remember, when I say plus, you can also use minus because the number could be negative. So how do we add these? Well, the way you think you would. If we were to add 3 plus 4i, we could write each one of them in parentheses and put a plus between them. Now, I'll admit that the parentheses in this addition problem are not necessary. They're simply there for emphasis. The only time parentheses are necessary is when there's something in front of them that has to be distributed. That's not the only time, but that's one of the main times it is. But here they're just for emphasis. If you really wanted to think about how to get rid of these parentheses, you can imagine that they're each being multiplied by 1 in the front, and then you could distribute the ones, but that wouldn't change anything. So we'll just say that when we're adding complex numbers, or more specifically, if you see a complex numbers in parentheses and there's nothing in front of it, or there's a plus in front of it, let me restate that. If you see a complex numbers in parentheses and the only thing in front of it is a plus, you can pretty much ignore those parentheses. All right, so how do we do this? Well, we could just erase the parentheses. It won't change what we're going to do. I'm going to put them back in, but you might as well see the problem like this: 3 plus 4i plus 5 minus 7i. Because if the parentheses weren't there, I think you would know what to do. This is just an issue of combining like terms. In this case, like terms means the 3 and the plus 5, I know what that equals, and plus 4i and negative 7i, I know what that equals. So you could say we're just combining like terms. But in the context of a complex number, you could say that we are adding real parts and adding imaginary parts. Recall that the real part of a complex number is the part of the complex number that doesn't have the I. In this case, 3 is the real part of 3 plus 4i, and 5 is the real part of 5 minus 7i. But you could also look at them as like terms. And what do we get when we add 3 plus 5? Well, we get 8. And we can combine the imaginary terms. Recall that the imaginary terms are the terms, the imaginary parts. The imaginary parts are the parts that have the i's. The imaginary part of 3 plus 4i is positive 4i. The imaginary part of 5 minus 7i is negative 7i. When we combine them, and when we combine like terms in general, you only combine the numbers in front, but you leave the objects that follow them the same. So the I is going to stay the same. What's going to change is the number in front. Positive 4 and negative 7 give you negative 3. So this means that 3 plus 4i plus 5 minus 7i is 8 minus 3i. So pretty simple stuff. I probably said a lot more than I had to, but I'd rather say too much than not enough. But let's summarize. Not sure what just happened there. There we go. To add two complex numbers, simply combine the real parts and combine the imaginary parts. Let me stretch this over a little bit further to put the comma at the end of the line. There we go. All right, so to summarize, and I'm going to highlight in the same colors that I did on the problem, to add two complex numbers, simply combine the real parts and combine the imaginary parts. But this is something you probably already knew prior to even hearing of imaginary numbers. You've heard of combining like terms before. All right, let's give one a try. Don't panic. I invite you to pause the video. Sorry, I need a fresh drink. I invite you to pause the video, and don't worry, it's nothing too bad. It's just Dr. Pepper. I invite you to pause the video and try this one. Now, the fact that it has fractions does not change your plan of attack. To add these complex numbers, you're still just going to combine the real parts and combine the imaginary parts. You should know the rules for adding fractions, but don't worry, we're going to review them here in a second. So pause the video, give it a try, and see if you can add these together. I hope you took the opportunity to try this problem, because just watching me do it is nowhere near as beneficial as trying it on your own first and either succeeding or making a mistake and learning from it. So let's give it a try. Let's start by combining the real parts. In this case, the real parts are 1/2 and negative 2/3. Now, if you need to take this to the side and work it out, there's no shame in that at all. So let's take it down here. 1/2 plus negative 2/3. And we could have just as easily written that as 1/2 minus 2/3, since adding a negative is the same as subtracting. Okay, what's the rule for adding and subtracting fractions? You should know that it is you get a common denominator and then you combine the numerators. To show you why, I'm going to write this problem slightly differently. I'm going to write it mostly in words, and I'm going to say minus instead of plus and negative. This problem is the same as 1/2 minus 2/3. And if you've never written fractions like this, where you write the denominator as a word, then you may have never realized why you have to get a common denominator. A fraction is really just a unit of measurement. In this case, the first fraction's unit of measurement is 1/2. There's one of them. And the second fraction's unit of measurement is 1/3, and there are 2 of them. If you view the denominators as units of measurements, then it makes perfect sense why we have to get common denominators, because you can't add apples and oranges. You can only add like things. To make a real quick example, and I do mean real quick, and then we'll go back to the problem. If I asked you to add, that was supposed to be drawn, but I can type it. If I asked you to add 1 nickel plus 1 dime, I'm pretty sure all of you are going to give me the same answer. You're probably going to say 15 cents. But if I get rid of the words, are you telling me that 1 + 1 is 15? Because good luck selling that. Of course not. Oops, come back. All right, I just made some stuff disappear. There we go. Are you telling me 1 + 1 is 15? Of course not. So if I were to ask you, where on earth did you get 15 from adding 1 + 1? I know what all of you would say. You would say, well, 1 nickel is 5 cents and 1 dime is 10 cents. And so what your brain was doing was converting those units of measurements, nickel and dime, to the same unit of measurement so that you could add those objects. Adding cents plus cents gives you more cents. To add a nickel and a dime, I have to convert them both to the same unit of measurement. Well, with fractions, it's the same thing. The only difference is the unit of measurement is often written as a number underneath the fraction bar. But if you think of it as words, like 1/2 minus 2/3, whatever a half is and whatever a third are, they're different objects. So in order to combine them, I have to make them the same unit of measurement. And in this context, that means getting the same denominator. So if you ever weren't sure why you get a common denominator, maybe that will shed a little bit more light on the subject. All right, now as far as getting the common denominator, keep in mind that the only thing you're allowed to do, there's only 2 things you can do in a fraction that will change its look but preserve its value. Those things are multiply both sides by the same number or divide both sides by the same number. So if I want to make these fractions have the same denominator, I either have to multiply both sides of a fraction by a number or divide. Multiplying will make numbers larger and we can turn them into lots of different numbers. In this case, we want to be able to turn 2 and 3 into the same number. That same number is 6. Anytime you have 2 fractions, you can always create a common denominator by multiplying their denominators. It may not be the least, but it will be common. Okay, so I'm going to get a common denominator of 6 by multiplying the first fraction on both sides by 3 and the second fraction on both sides by 2. Let's see what that changes the problem to. In the first fraction on the top, let me highlight where I'm talking so that you can follow me. In the first fraction on the top, we have 3 times 1, but 3 times 1 is just 3. And in the first fraction on the bottom, well, we know what we get because we were shooting for a common denominator. 3 times 2 is 6. So 1/2 is the same as 3/6. Plus, in the second fraction's numerator, we have -2 times 2, that's -4. And in the second fraction's denominator, we have 3 times 2, which of course is going to give us 6. And now if I were to write this problem in words, and I'm really going overboard at adding these fractions, but I know that a lot of people have trouble with fractions, and hopefully this will help you understand them and be able to work with them again in the future. But if I were to write this problem in words, it would be 3/6 minus 4/6. And now I'm adding apples and apples. Whatever a sixth is, when I have 3 of them and subtract 4 of them, I end up with -1 of them, but they are still sixths. Apples plus apples equals apples, but in this case, apples means denominator. All right, so that's why you add fractions the way that you do. All right, so keep the denominator of 6. 3 plus -4 is -1. And when we add 1/2 minus 2/3, when we add 1/2 and -2/3, we get -1/6. I know that was a lot of talk just to put together 1/2 and -2/3, but I wanted to take this opportunity to remind you how to add and subtract fractions. We'll go through the second one a little bit faster. All right. We are now going to combine the imaginary part. So we're going to combine the -3/4 I plus the 1/3 I. Now I know that these are going to give me I's, so I can actually write down the I already and just focus on the fractions. -3/4 plus 1/3. And again, I've already got the I accounted for over here, which is why I didn't write it down there. All right, we're back in the same boat. We're adding fractions and we need a common denominator. If you don't know what it is, just use the product of the denominators. 4 times 3 is 12. I'm going to turn both fractions denominators into 12. The first fraction, I'll multiply both sides by 3. Second fraction, I'll multiply both sides by 4. I'm not going to do all the highlighting I did on the previous one. I'll just call out where I am. In the first fraction on the top, we have -3 times 3, that's -9. In the first fraction on the bottom, we have 4 times 3, which is 12, and then plus. In the second fraction on the top, we have 1 times 4, which is 4. And in the second fraction on the bottom, we have 3 times 4, which is 12. Now our fractions have common denominator of 12, so that will be the denominator in the final result. And in the numerator, -9 plus 4 is -5. And so -3/4 plus 1/3 is -5/12. That is the imaginary part of our answer. Notice that when I wrote the -5/12 in front of the I actually put the minus in front of the fraction, whereas it used to be on top with the 5. And the main reason I did that is because I knew that my answer was either going to have a plus or a minus in the middle. Because it was negative, I wrote the minus. So 1/2 minus 3/4 I plus -2/3 plus 1/3 I is equal to -1/6 minus 5/12 I. Piece of cake. Again, the concept of adding complex numbers is pretty straightforward. We're just combining real parts and imaginary parts. Whether they're fractions or not doesn't matter. All right, let's talk about subtraction of complex numbers. The thing on the bottom wasn't supposed to be showing up yet. Oh well, didn't mean to spoil the surprise for you. There you go. All right, so we're going to subtract 2 minus 3i from 7 plus 5i. Now, I thought about just writing this as a problem without words like I did there, but I noticed that some people, when they do subtraction problems, when they go from words to symbols, sometimes struggle with the correct order in which to write the subtraction problem. When you say subtract one thing from another, the from number is what you start with. Start with this. Let me take that font size down a notch. But anytime you have a subtraction problem in words, I want to subtract this from that. Whatever you're subtracting from is the number that you write first. So in this case, we're going to start with 7 plus 5i. And notice that I put parentheses in it. That was mainly for emphasis, but the next one won't be just for emphasis. From that, we're going to subtract the other one, which is 2 minus 3i. Now, when you're subtracting complex numbers, and more generically, when you're subtracting objects that are larger than a single term, you can think of a complex number as having two terms, a real part and an imaginary part. It is critical that the second object being subtracted is in parentheses. Why? Well, look at the problem as is. You see the minus in between the parentheses? What does it belong to? The answer to that question is always whatever is immediately to its right. This minus belongs, that was supposed to be red. This minus belongs to that parentheses, which means it belongs to whatever is inside those parentheses. So the minus belongs to the entire 2 minus 3i. If I did not write parentheses around it, now who does the minus belong to? Well, the answer is whatever is immediately to its right, which is the 2. Now it only belongs to the 2. Only the 2 is getting subtracted. The minus 3i is not getting subtracted. So again, when you are subtracting objects, if those objects contain multiple terms or multiple parts, then the second one, the second part of the subtraction problem, the thing you're actually subtracting, needs to go in parentheses. Now in your homework, I believe the parentheses are already set up for you. I just wanted to make that, clarification. All right, so how do we do this? Well, in short, we combine like terms, but in algebra, when you're combining like terms, you have to be careful when those terms are inside of parentheses, because if they are inside of parentheses, there may be something to the left of the parentheses that is preventing them from escaping the parentheses, so to speak. In this case, the first parentheses has nothing to the left of it, nothing right here. So the first parentheses I can pretty much just ignore. However, the second parentheses have this minus in front of it. So I cannot gain access to the contents of the second parentheses because the minus is there holding those parentheses in place. but I need to gain access to the contents of the second parentheses so that I can start combining like terms. How do you fix this? The answer is easy. When you have something in front of parentheses and the contents of the parentheses are multiple terms, let all that sink in. When you have something in front of parentheses like this minus sign, and the contents of the parentheses contains multiple terms, in this case, a 2 and a 3i with a minus in between, then you can and probably should invoke the distributive property. The distributive property says multiply whatever is in front of the parentheses times each individual term inside the parentheses. Now you may be asking, how do I multiply by negative? But think of it, that's like multiplying by -1. In the second parentheses, I'm going to multiply each term by -1. First parentheses, there's nothing in front, so I can drop them right now, 7 plus 5i. In the second parentheses, I'm going to distribute the negative to the 2 to get -2. And I'm going to distribute the negative to the minus 3i. Well, what's a negative negative? A positive. Minus 3i is the same as a plus 3i. And notice that the terms in the second parentheses appear to have changed signs. There used to be a +2 in the parentheses. Now it's a -2. There used to be a -3i in the parentheses. Now it's a +3i. Now it's a +3i. In general, if you ever see a negative in front of parentheses and the parentheses has multiple terms, you can distribute the negative to each term in the parentheses, and the effect is it changes each of those term signs. Now, at this point, we're ready to combine like terms because there are no parentheses keeping things trapped. And now we just got to track down our like terms. Well, this is the easy part. For the real parts, we have, figure out what color I use back here, green for the reals. We have 7 minus 2, that's 5. And for the imaginary parts, we have +5i and +3i, that's +8i, finishing the problem. And again, this is actually a faster problem to do than it is to explain all the intricate details. But it would be nice to summarize what we just did. And that's what's underneath that white box at the bottom. To subtract complex numbers, all you have to do, change the signs of the second complex number because it's the one with the minus in front of its parentheses, and then combine like terms. So essentially you turn it into an addition problem. All right, let's try one and then we'll move forward. I got a couple of more problems after this next one. So 3 more. This one shouldn't surprise you. Subtract the following. Parentheses, open parentheses, 3/4 plus 5/4 I, close parentheses, minus open parentheses, -5/4 plus 1/4 I, close parentheses. Yes, it's more fractions, but if you look closely, this one's actually easier to start. I invite you to pause the video and try it. I'll give you a hint. They all already have common denominators. Did you pause the video and try it? If you did, great. If you didn't, why not? I'm giving you an opportunity to try the problem before I go through it. See if you can beat me to the answer. If you haven't tried it, this is your last chance to pause it because here we go. All right. This is actually pretty straightforward. First, when you subtract complex numbers, you change the signs of the second complex number because of the minus in front of its parentheses. What does that leave us? Well, in the first complex number, we can lose the parentheses. There's nothing to the left of them to require the parentheses to be there, or you could think of it as distributing 1. And in the second complex number, the minus gets distributed and change the signs of the terms in the second parentheses. The first term in the second parentheses was -5/4. Now it's +5/4. The second term in the second parentheses was +1/4 I. Now it is -1/4 I. And now we just have to combine like terms. Well, the real parts are 3/4 and +5/4, which already have a common denominator of 4. So that makes it a little bit easier. All we have to do is combine the numerators. 3/4 plus 5/4 is 8/4. That looks like we should do something with it, and we will, but let's go ahead and finish combining like terms by combining the imaginary parts, positive 4i and negative 1/4 I. Those are going to give me my i's. Now I just have to figure out what is 5/4 minus 1/4. Well, the common denominator is 4, and then 5 minus 1 is 4, and more specifically positive 4, hence we have a plus in the middle. So we've subtracted them, but because the results are still fractions, we should consider reducing them. I did not mention that previously because the fractions in this answer did not reduce. Negative 1/6 will not reduce. Negative 5/12 will not reduce. But in this problem, not only do these fractions reduce, they flat out disappear. All a fraction is a division problem. The first fraction says 8/4, which is the same as 8 divided by 4. 8 divided by 4 is 2. Plus, and in front of the I, we have 4 divided by 4, which is 1. So we get a final answer of 2 plus I, or we could just say 2 plus I. We got a final solution of 2 plus 1i, or we could just say 2 plus I because the 1 is understood to be there. Anytime you don't see a number in front of a letter, you can almost always assume it's a 1. All right, so that wasn't too bad. The last two examples are just a longer problem and a more general problem. It's a, dare I say, proof. You'll see when we get there. All right, simplify the following. The good news is I took out all the fractions. The bad news is there are 4 complex numbers, some with minuses in front. The number of complex numbers we're combining doesn't change the rules. If there's a minus in front of a complex number's parentheses, we distribute it, essentially changing the signs of all the terms. And once that's done, we combine the real parts, combine the imaginary parts. I invite you to pause the video, see if you can do this entire problem all the way to the end. Did you try it? If you didn't, why not? All right, if I were doing this, which I'm about to do, I would start by dealing with all the parentheses with minuses in front. The first complex number, 4 minus 5i, has no minus in front, so it's good. The second one, wait a minute, let's take it one at a time. The first complex number does not have any parentheses, does not have a minus in front of its parentheses, so we could just drop the parentheses. The second complex number, 10 minus 3i, is preceded with a minus in front of its parentheses. That minus will get distributed and change the sign of the 10 and the sign of the minus 3i. So the positive 10 becomes negative 10, and the negative 3i becomes positive 3i. The third complex number, 1 plus 7i, is in parentheses and is preceded by a plus. But that's okay. We can just ignore everything. Or if you want to be consistent, distribute the plus. That's like multiplying by positive 1. But multiplying something by positive 1 doesn't change anything, so it's kind of silly. So the 1 stays positive, and the 7i stays positive. But the last complex number, 5 plus 5i, is preceded by a minus in front of its parentheses. Therefore, that minus gets distributed, changing the signs of the terms inside of the last parentheses. 5 becomes negative 5, plus 5i becomes minus 5i. Now that we busted everything open, all we have to do is track down like terms and combine them. Just cleaning that up a little bit. And when it comes to adding complex numbers, that means finding the real parts and finding the imaginary parts, which are easy to find. The real parts don't have i's. 4 minus 10 plus 1 minus 5. Those are all the real parts. What do we get when we put all those together? Well, 4 minus 10 is negative 6. Negative 6 plus 1 is negative 5. Negative 5 minus 5 is negative 10. The real part to our answer is negative 10. Then track down all the imaginary parts, which are all the remaining parts. They all have i's. Minus 5i plus 3i plus 7i and minus 5i. Let's attack it from left to right. minus 5i plus 3i. You know what? Forget the i's. We'll just write it here. We'll add the numbers and stick it in front of the I, because they're all like terms and it's going to end up with an I anyway. So let's just focus on the numbers in orange. Negative 5 plus 3 is negative 2. Negative 2 plus 7 is positive 5. Finally, positive 5 minus 5 is 0. Wait a second. Let's make sure that happened right. This time I'll keep track of where I'm going. Remember, we're only focusing on the numbers right now. Negative 5 plus 3 is negative 2. Negative 2 plus 7 is positive 5. Positive 5 minus 5 is still 0. 0 is neither positive or negative, but you can put plus or minus in front. I prefer plus. So we end up getting negative 10 plus 0i. Okay, it happens. Now, is this an acceptable answer? Yes. Is it correct? Yes. Is it the most simplified answer? No. Because whenever a complex number has a 0 for its real part or imaginary part, it's kind of silly to say that it's there in the first place. Negative 10 plus 0i is just the same as negative 10. Because how many i's does this negative 10 have attached to it? 0. If it had been reversed and it wasn't, but had it been reversed and said 0 minus 10i, then we could have just said minus 10i. Anytime either part is 0, it's not necessary to list it. All right, everything you've seen so far is what you're going to be held accountable for in your homework. This last example is just kind of a bonus and extension problem. If you're just worried about homework, you can stop the video here, you're going to be fine. But if you're trying to make your brain work better and trying to become a better problem solver, I invite you to hang around for this last example. Prove that the sum of any complex number and its conjugate is a real number. Excuse me, typo in there. Prove the sum of any complex number and its conjugate is a real number. Well, first off, there's no problem that I gave you here, no numbers to work with, no positives or negatives or anything. And secondly, I'm bringing up the word conjugate, which was defined in the first video in this series. So just as a reminder, recall the conjugate of a complex number is the complex number with the same real part, but the opposite imaginary part. So for example, if I gave you something like negative 7 plus 5i and asked you what its conjugate was, it has the same real part, so it has negative 7, but the opposite imaginary part. So instead of positive 5i, I'd have negative 5i. And we're trying to prove that the sum of a complex number and its conjugate is real. Well, what happens if I add these together? The imaginary parts cancel because they're opposites, and negative 7 plus negative 7 is negative 14, which is real. So does that prove that the sum of any complex number and its conjugate is a real number? No. What it proves is that the sum of this complex number and its conjugate is real. So how do you prove that something is true all the time, not just for a specific case, like for negative 7 plus 5i? The way that you prove something is you remove all the specificity from it and try to play it out as generically as possible. When I showed you the example of negative 7 plus 5i, adding it to its conjugate and getting a real number, that's a specific example. That's a specific real part, negative 7. That's a specific imaginary part, positive 5i. So how do we do this generically? Well, we replace the specific numbers with generic numbers, aka we replace the specific numbers with variables. So how would a proof go? Well, a proof would go something like this. Let me go inside of here and type it. We're going to say let a plus bi be any complex number. That's a good place to start. Because if we're going to prove something for any complex number, we should start by identifying it. Okay, so we have any complex number. How would we write its conjugate? Well, by the definition of conjugate, we have the same real part, so it would still start with a, but the opposite imaginary part. So if our imaginary part on the generic complex number is plus bi, then the imaginary part on its conjugate is minus bi. So now that we've generically represented a complex number and its argument, so we can now look at their sum. A plus bi plus a minus bi. So there's the sum of those two numbers written. And at this point, it doesn't take too long to figure out what's going to happen. None of the parentheses are necessary because the one on the left has nothing in front of it. The one on the right has a plus in front of it. That's like a +1. Multiplying by +1 doesn't change anything. So we can essentially drop all the parentheses and write a plus BI plus a minus BI. Well, you see what happens? The BI's cancel just like they did in the specific example. And we're left with an A plus another A. Well, A plus A is 2A, which is a real number. How do we know it's a real number? Because when we define the original complex, the generic complex number at the beginning, recall that the definition of a complex number says that the A and the B are real. And so when we add the number to its conjugate and get 2 times A, if it didn't have an I before, doubling it won't give it an I now. Proof is done. Adding a complex number to its conjugate will always give a real number. That's the end of this video, but I want to foreshadow something that's going to happen in the next video. The nice thing about a complex number and its conjugate, not only is the sum of them real, but so is their product.